Let's take a moment now to learn about limiting reactants, a specific kind of stoichiometry problem. If you haven't already learned the stoichiometry lesson, you should go back to that last lesson before watching this video. In this photo, we see a production line of an automobile company. But what do you think would happen if they ran out of engines at this plant? Obviously, production would stop. Well, chemical reactions are no different. When one of the required chemicals runs out, production also will stop. That chemical is called the limiting reactant. A limiting reactant is defined as the substance that runs out first. It limits production. The other reactant is known as the excess reactant because it is present in excess. So when the reaction is done and production has ceased, there's still leftover excess reactant. Sometimes a reaction is performed using stoichiometric proportions. This simply means that both reactants will run out simultaneously. This is the ideal way to run a chemical production plant because there are no wasted reactants. So let's look at a simple analogy. We're going to talk about making trikes from their parts. These trikes will be assembled from wheels, frames, and pedals. Based on these pieces and their symbols, let's try to write the chemical formula for a trike. That's 3 wheels connected to a frame that also contains 2 pedals. So the formula is W3F-P2. And if we want to show the production of these trikes using a chemical equation, we would write 3 W's plus 1 F plus 2P yields 1 W3F-P2, or 1 trike. Notice in this equation that there are ratios built in. For example, it takes 3 wheels to make 1 trike, while it takes 2 pedals for every 1 trike. So here's a question. How much product could you make given the following materials? This is an interesting question, and the answer depends on how you calculate. If your calculation is based on wheels, your problem might look like this. I have 24 wheels. I want to know how many trikes I can make. The wheel to trike ratio is 3 wheels for every 1 trike. Therefore, I can make 8 trikes. But if you said 8 trikes, you would be wrong. Now let's look at the other parts. Using the frames, we can perform a similar calculation. There are 10 frames, and they react with a ratio of 1 frame for every 1 trike. We cancel the units of frames and discover that we can make 10 trikes. However, neither of these answers is correct. Let's look at the pedals. The math for the pedal calculation looks like this. I'm given 14 pedals. I set up a pedal to trike conversion, which has a ratio of 2 to 1. This gives me 7 trikes. Well, now this problem has become more complicated. I have 3 answers. Is it 8 trikes? 10 trikes? 7 trikes? Is the answer the sum of these answers? 25? Do I need to take the difference? What do I do with all these numbers? What you may have done when you answered this question is that you picked the smallest number because you realized that once the pedals were gone, you can't make any more trikes. So you don't add or subtract these answers, you pick the smallest number. And we'll do the same thing with our chemical calculations. One thing I'd like to point out is that you can't identify which reactant will limit the reaction simply by picking the item present in the smallest amount. Just because the frames are the smallest amount, this doesn't mean that they run out first. And that's because different reactants get used at different rates. Now, let's look at a chemical example. This question says, how much product could you make with 28 grams of nitrogen and 18 grams of hydrogen? The first question is, how do we even know this is a limiting reactant problem? How is this problem different from other stoichiometry problems? Notice this problem has 2 givens. The second question is, how do we approach this problem? How do we solve a problem with 2 givens? We would solve this problem like the trike problem. We'll do 2 calculations using both of the givens, and then we'll look at our answers and see which one made the least amount of product. This can tell us which reactant was limiting and which was excess. Let's try one of these calculations now. I have 85.5 grams of iron 3 oxide and 15.7 grams of hydrogen. What mass of iron is formed? And what is the limiting reactant? I like to write down what I know about each substance near its formula in the balanced equation. I also make a note of what I'm looking for. This helps me see that I'm doing a limiting reactant calculation. So we do two calculations using each of the givens. The first problem is based on the iron oxide, and I have 85.5 grams of Fe2O3. From that amount, I'm trying to calculate the grams of iron that can be produced. The second problem will be based on the amount of hydrogen, 15.7 grams. In this problem, I'm looking for the same thing, how many grams of iron can be formed. Now, I will fill in the stoichiometry problem. I put grams Fe2O3 on the bottom and moles Fe2O3 on the top. The number here comes from the periodic table and is 159.69 grams per mole. The next step is the mole-to-mole ratio, and the numbers come from the balanced equation. And finally, the last step, where I'll convert moles of Fe to grams of Fe using its molar mass, which is 55.8. For the second problem, I will do something similar. In this step, I convert from grams of hydrogen to moles of hydrogen using the molar mass on the periodic table. Next, I insert the mole-to-mole ratio. This ratio is 3:2. And finally, I convert moles back to grams, and the molar mass again is 55.8. All units cancel, and the answer is 292. So I have two answers. What do I do with my answers? Do I add them or subtract them? No, I simply report the smaller answer, just like I did when calculating trikes. So which substance limits the reaction? The iron oxide, which means the hydrogen is the excess reactant. Let's try one more. This problem says what volume of hydrogen gas will be produced from the reaction between 39.1 grams of potassium and 36.0 grams of water. Assume standard temperature and pressure. I'm going to write down all pertinent amounts next to my problem. We will perform two calculations based on the amount of potassium and the amount of water. In each calculation, we will find the liters of hydrogen. This time, I'm going to set up the units in my calculation first. First step in a stoichiometry problem is always to convert to moles, unless, of course, we are given moles. The second step is to insert the mole ratio, converting in each problem into moles of hydrogen. And in the last step, I convert from moles to liters. The first step was a grams to moles conversion, and is called the molar mass. Look this up on the periodic table. The next step goes from moles of one substance to moles of another, and is called the mole-mole ratio. It can be found in the balanced equation. The final step, we go from moles to liters, and this is called the molar volume. At STP, the molar volume is always 22.4 liters for every mole. Now, let's put in those numbers. For potassium, it's 39.1 grams per mole. The mole ratio is 2 moles of potassium for 1 mole of hydrogen. The molar volume is 22.4 liters per mole. And in the second calculation, the molar mass of water is 18 grams per mole. 2 moles of water react for every 1 mole of hydrogen. And then the molar volume, which is 22.4 liters per mole. Now we'll go back and check units, and then do the math. In the first problem, I can also cancel the 39.1. This leaves 22.4 over 2, which is 11.2. In the second problem, we can simplify. 18 into 36 is 2, and the 2's cancel, leaving 22.4. And I have two answers. Which is the correct answer? The smaller answer, 11.2 liters. So the limiting reactant is potassium, and the excess reactant is water. That's how you solve a limiting reactant problem. Have fun!